Hello. Am I audible?
Sir. Yes, sir, audible.
Is it clear? Is there any disturbance?
No, clear, sir. Sir,
If it is clear, then we'll proceed.
we'll start
We
in
can start.
2 minutes. We'll start in 2 minutes. Everybody will be joining because the
Okay,
first
but,
session was delayed. It was finished at 1:15 for 20. So we wait for 2 minutes. After that, we'll start.
Okay, I'm trying to join through my mobile also, but that is not actually showing that.
Sir, if you say I can present your presentation, no issue.
Right, there is a problem with the speaker here. If I'm able to.
Yeah, sir, your voice is clear.
Okay, then no problem. Then no.
Okay.
If
Sir,
not clear, just let me know.
Sure, sir. We'll start in 2 minutes. I'll be telling you, sir. Thank you.
Is PPT visible?
Yes, sir.
Is it full screen now?
Now it is full screen. Data science pre-post process.
If there is any difficulty, just let me know in between also. You can stop me.
Sure, sir.
Whenever you want to start, then I will start.
Sure, sir. Good afternoon, everyone. We'll start second session of first day of FDP, AICT ATAL FDP program. So in second session, we have
Just hold on. I'm changing the device.
Okay, so we'll start with the second session. The speaker for second session is Dr. M.S. Rao. He is currently professor and head Department of Chemical Engineering, Faculty of Technology, Dharamsi Desai University, Nadiyad. Professor Rao obtained his BTech degree from JNTU College Engineering Anandpur, MTech from MS University Baroda, and PhD from IIT Bombay. Dr. Rao received Excellence in Research Award for his PhD thesis at IIT Bombay. He has supervised 6 PhD projects, guided more than 50 MTech projects. He has also successfully completed more than 200 industrial consultancy, research, and audited projects. He was elected and served as a 6 year as a member of National Executive Council of II Chemical Engineering Executive Council. He has more than 25 years of teaching and industrial experience. With this brief intro, I'll request Dr. M.S. Rao to start with his presentation. Sir.
Okay, thank you for your good words. Uh, Let me start my presentation. So the topic for today's presentation, am I audible to everybody?
Yes, sir.
Okay, then I am proceeding. Okay, the topic for today is data science, pre-processing and post-processing of data, followed by artificial neural networks. So overall presentation will be as follows. First, I'll try to introduce to you about the artificial intelligence, data science. There are some key words involved in this. I'll try to introduce them first to you. Then I'll try to talk about database modeling, what it requires to model a particular process, and certain difficulties associated with the data. Whenever we are trying to develop mathematical model or otherwise any such model, we require to use data, but the data will not be in a proper form. So how to convert that data into required form? That's what actually I'll discuss over there. Then I'll try to discuss about how the database models are being developed to use as artificial intelligence conventionally. So to say, in starting from 1840 to approximately 1950, they use regression followed by artificial neural networks. In last decades or so, people are start talking about machine learning and deep learning, etc. I'll try to introduce those terms first to you. Then I'll try to give you brief introduction about artificial neural networks. What is this artificial neural networks all about? What are the fundamentals of these neural networks? What are the various type of artificial neural networks? I'll try to introduce those things in brief. Okay, the first part is why do we need to study this first of all, and then I'll try to introduce to you what is artificial intelligence and data science, followed by modeling, then artificial neural network. Let's start with the first part, that is introducing some of the words which we normally hear from people. So artificial intelligence is basically knowledge gathering, reasoning, perception, learning of prior assertions, and come to the conclusion. So you must have heard about fuzzy logic based washing machines. So that is basically artificial intelligence. Now, when you put few clothes in the washing machine, it decides how much water has to be taken. So this intelligence is not given by you. Actually, it has been developed based on the data which is existing currently and based on the reasoning, etc. Basically, what we are doing there is creating intelligent systems which can take decisions without the human interference. So that is known as artificial intelligence. So next one is in artificial intelligence nowadays we are hearing few words, ANI, AGI, and ASI. Let me tell you what they are all about. Artificial narrow intelligence. For example, the example which I have given to you, that is the washing machine example. Uh, the mathematical model which is being developed to take care of water intake based on the weight of the clothes which you are putting in the washing machine is related to that particular system only. So the knowledge as well as intelligence what we are talking about, which we have developed to take care of that particular system, is related to a particular system itself. So this is narrow knowledge. You cannot use this knowledge for something else. So that is called as artificial narrow intelligence. So this is being developed for quite a few years now. We can say 1950s, 60s we started with, and then still we are dealing with narrow intelligence itself. So the next step towards this is artificial intelligence is artificial general intelligence. What is this? This is having best possible skill and knowledge in every domain of possible requirement of artificial intelligence. So for example, when you are trying to drive a vehicle, you must have every knowledge. And so what is going to happen in future, what is actually happening with the fuel tank, what is happening with the accelerator, what is happening with the brake, and that too the maximum possible knowledge. This is difficult to develop. So this is interdisciplinary thing. You need to have maximum knowledge in all the fields, which is not possible as of now. So people are trying to develop this. So this is basically artificial general intelligence expected to reach this stage somewhere near 2030. We are not sure whether we'll be reaching there or not. So that is what we are talking here in case of artificial general intelligence is attaining maximum possible skill levels and the knowledge levels into the systems. So that's what actually we are striving for. Next thing is artificial super intelligence, that is better than humans. So machines are overtaking the human beings in all possible fields. That's what it is. So probably we are not at that stage of now. We may reach that stage after some time. But once we reach artificial general intelligence, it's not going to take much time to reach artificial super intelligence, because general intelligence will take into super intelligence very fast. So basically, artificial intelligence is knowledge gathering, reasoning, perception. Based on the prior knowledge, we try to develop mathematical models and try to use those models to take decisions in our place. The next buzzwords are artificial intelligence, machine learning, artificial neural networks, and deep learning. What are these things? Machine learning is the process of applying artificial intelligence. Here, basically, we employ machine learning includes decision trees, artificial neural network, regression. Okay, so what is that we are trying to do? Provide systems with the ability to learn and improve prior experience towards the performing a given task. So machines are learning certain things and then trying to take decisions in place of human beings. That's what we call it as machine learning. Artificial neural network is a part of machine learning only. What we try to do here, in this case of artificial neural network, is we try to mimic human brain. So mimicking the human brains is basically, human brains are made of neurons. We to replace those neurons with certain mathematical functions and try to use mathematical functions in place of neurons. So that's what actually artificial neural network all about. We're going to discuss about that one in detail after a few slides. Okay. At the end of this lecture, you will be familiar with what is meant by artificial neural network. Then comes deep learning. That's what actually we are hearing for the last few years. Deep neural networks. This is basically artificial neural networks only with quite a few hidden layers of neurons. You may not be familiar with what is this hidden layer, input layer, output layer, etc. By the end of this lecture, you'll come to know about that. Basically, what we are trying to use in case of artificial neural networks is basically we are trying to use functions, layers of functions. In case of deep neural network, we are using quite a few hidden layers, and then we are trying to develop algorithms in each one of the layers to get the final outcome. So with this brief introduction about artificial intelligence and artificial intelligence, machine learning, neural networks, and deep learning. So basically, trying the multi-layered neural network is called as deep learning. So you may be having recurrent networks and then belief networks, etc. in this category. Let's look at recent journal, that is Nature of the top journal. What it says. One of the articles I was going through 2 days back. So you can read the paragraph. This paragraph says what they have done is they have taken a few samples for healthy human cells and damaged human cells. They are subjected to some kind of variation in the sugar level and oxygen level. Try to look at what is that variation is going to cause with respect to the outcomes like a lipid, metabolite, enzyme, etc. So if you're able to understand this in a nutshell, in a layman's language, we can say this: levels of sugar is varied, levels of oxygen is varied. They are trying to study what is its effect on the lipid profile, metabolite profile, enzyme profile, and protein profile. By looking at this, they are trying to take the decision what has to be done with the cell, whether the cell is really damaged or not. So this is what actually getting the input data, getting the output data, trying to map these two data. So analyze the profiles of healthy and diseased cells, then decide the treatment. So by looking at this, what we have done is change sugar concentrations, otherwise oxygen levels, and then they are causing some variation in the profiles of lipid, metabolite, etc. In a given cell. If the cell is healthy, the profile is different. If the cell is damaged, then the profile is different. So based on that, we are trying to take the decision. Who is going to take the decision? Say human beings are taking decision. Now we are trying to replace these human beings with machines. That's what is artificial intelligence all about. So what they are saying further in the same paper is they are trying to turn down the drug discovery paradigm. So what they are trying to do is patient-driven biology and data to drive more predictive hypothesis. Of course, you can read this later on. I'll show you what they have done, basically. So they try to change the levels of sugar, levels of oxygen. They try to study the profiles of lipid, metabolite, enzyme, protein profiles, etc. This thing they have done for the healthy cells and diseased cells based on the profiles what we are having on our hand. After studying this, they try to decide whether the cell is damaged or not, healthy cell. So this, by looking at all these profiles and graphs and all, a human being decides. Now we wanted to change this human being by putting a machine over there. You are inserting all this data, what you have done with respect to the levels of sugar and oxygen, what you got in terms of profiles, all of them are given to the machine, and now machine says that, okay, this particular profile is changing in appropriate manner, otherwise inappropriate manner. So I can decide that this is a healthy cell, this is a diseased cell. If at all this particular profile is getting changed, the healthy cell is becoming unhealthy, otherwise diseased one, but that particular disease may be because of this. This kind of decision is being taken by the human beings as of now. We are trying to use algorithms to take such decisions. That is actually artificial intelligence. So this is what actually I wanted to introduce to you. Basically, what we are trying to do is we are trying to replace this human mind with machines. How do you do this? In this, from where this data science comes into picture. What is data science, first of all? An area that manages, manipulates, extracts, interprets knowledge from the tremendous amount of data. So if you look at the example which I have given to you earlier, what they have taken 1,000 samples. So you can say here, more than 1,000 cancers and healthy human cells they have taken. 1,000 is a very small way to decide anything in AI parallels. So the data which we are talking about here, a huge amount of data which is available on the net, and then health records, etc. Try to develop artificial intelligence, use that artificial intelligence to take decisions. That's what actually is nothing but your data science. So this is basically a multidisciplinary field. It need not be only health records or drug delivery or drug development. So it can be anything else. So you got huge amount of data, use the data to take decisions. That is basically picking up the data, modifying the data to your requirements, use the data to develop mathematical models, otherwise relationships between input and output, and try to use it in future. That's what basically data science all about. So probably at this stage you may be wondering, what is this data science? It's actually looking abstract. Let me give you one more example to talk about. See, artificial intelligence, people are using this word nowadays very in a fancy manner. If you look at the 19th century, like 1800 and up to 1950 or so, what people did is they tried to relate the input and output. For example, if you are changing something, based on that, how the outcome is changing. Let me give you a simple example. If I have a simple tank, water is falling into the tank. If I increase the inlet flow rate, obviously water level goes up. If I decrease the inlet flow rate, water goes down. So we are trying to develop a relationship between the height of the liquid in the tank and then inlet flow rate. So if you have quite a few flow rates and then corresponding heights, you can develop a relationship. That relationship can be a straight line, but the data what you got may not be sitting on the straight line. You can see here. So this kind of developing a relationship between the input and output with the available data is called as regression. Tomorrow, if somebody asks you, if I increase the flow rate from this to that, for example, if I increase the flow rate by 20%, what is going to be its effect on the level of the liquid level in the tank? So then you need not bother about your using your brain. You already got the mathematical model. You plug in there, it will give you the information. What we are essentially doing is we are replacing the human being, and decisions which are taken by the human being is taken based on the mathematical model outcome. That is basically we call it as regression. I'll elaborate a little more on that. But the problem with the regression is mostly it is linear, but input and output relationships may not be linear in most of the cases. Maybe in chemical engineering, maybe in biotechnology, many other fields, the input and output are not related in a linear manner. If they are related in a non-linear manner, that too complex non-linearity, In that case, you cannot try to use RN. So they have gone for nonlinear relationships. So to say, artificial neural networks is one such nonlinear relationship or one such model which is giving you the relationship between the inputs and corresponding outputs. So then they try to replace human beings with decisions taken by the neural networks. Otherwise, outcomes of the neural networks are being used in place of decisions taken by the human beings. If that is the case, then we call it as a artificial intelligence. Of course, there is one more thing which is being used almost in parallel to these artificial neural networks is fuzzy logic. So that also does the same thing. But what I'm going to concentrate today is only on artificial neural networks. Okay. Before going for that, let me elaborate a little more on regression. So what is artificial intelligence here? What it does? So it basically tries to look at the relationship between the input output. For left, we have 4 figures. I'm talking about the left top figure where regression is being written. So what we are trying to do is we are trying to develop a relationship between the variable which is there on x-axis and y-axis. The next one is classification. So the data which is there above this line is classified into yes, and below this line no, or vice versa. But we are trying to classify the outputs whatever we have seen there based on some information which is available. So here in this case, we are aware of where this straight line is lying. The other case is we are not aware of any straight line or something like that. When you got the outputs, you got outputs clustered somewhere here and there. For example, the third figure, that is left bottom, you can see there are red signs, there are squares, there are triangles. You can clearly see that they are clubbed together at some place, but they are actually forming 3 distinct clusters. So these are called as clustering. So the third one is anomaly detection, means if you are aware of, if you increase the flow rate, level is going to increase. If you decrease the flow rate, level is going to decrease. All of a sudden, when you decrease the flow rate, level has increased. Means some abnormality has happened. Or otherwise, if you increase the flow rate, level has decreased. Means some leakage has taken place. So there you try to find out, is there any anomaly which is happening contrary to what is actually supposed to happen. This is called as anomaly detection. So these are the things normally being used in case of artificial intelligence in conventional terminology. So artificial intelligence is being used for this purpose. First one is regression, classification, clustering, and anomaly detection. That's fine. Now, so what is our target? When in case of artificial intelligence or data science, what we try to do first? We try to relate the inputs and outputs. The input may be inlet flow rate, output may be liquid level height. Okay. In some other case, input may be some heat which you are supplying through electrical heater. Output may be temperature increase or decrease in the water. So the relationship between input, which I am designating it as U, the output, which I am designating as Y, the input and output relationship can be either a linear one or it can be a non-linear one. So for example, Y is equal to mx is a linear relationship. On the other hand, Y is equal to A into e raised to B of x. That is, A is a constant, exponential, B of x. So you are taking something, a relationship between Y is equal to e raised to x. If you write, that is an exponential relationship, which is no more non-linear, linear one. This is non-linear relationship. In addition to this, the data available for us may be continuous in nature. It can be discrete in nature also. In other words, if you're asked to take some data, for example, temperature you are measuring of a human being, and you are noting it down also. Then the data which you are showing to the other person, when he is asking you whether you have collected the data or not, are few numbers. What those numbers are meant for? At 10 o'clock, you have taken one data point, 10 o'clock, 1 minute, another data point, 10 o'clock, 2 minutes, another data point, so on and so forth. So there is some lapse of time in between taking 2 data points. So you have data, of course, related to a continuous process, but the data is discrete in nature. It has some time gap, time period lapse in between. So when you're trying to develop relationship between input and output by using the data which you are collecting after some time intervals, that is known as Of course, so that is known as a discrete time mathematical model. If you reduce the time period to very, very small, then it is called as a continuous time model. So the mathematical relationship which we are trying to develop between the input and output can be either a continuous one or a discrete one. In any case, when you are trying to develop these relationships, you require input data and output data. This is where actually data thing comes into picture. So let's try to look at this data, what kind of data we are talking about. So what kind of data is necessary also. Here in this case, what are possible models? There are various type of relationships which you can develop between the input and output. If you are having perfect knowledge about the subject, in that case, you can develop mathematical model based on the first principles or otherwise fundamental understanding about the subject. That kind of mathematical models are known as first principle models, or otherwise they're also known as white box models. Here in this case, we are using mass balances, energy balances. This is what actually you see in fundamental engineering principles. The next area of mathematical models are gray box models, wherein you have some understanding about the system and some data available with you. You try to use both the categories of information to develop mathematical model. The third one is a very complex system. You know nothing about the system. All that you know is you are giving some input and you get some output. Based on that input and corresponding output, you are trying to develop a relationship between these two. This is completely input and output data based mathematical model development. These kind of models are also known as black box models. So in data science, in most of the cases, what we are trying to develop the relationship between input and output are essentially these black box models. So these black box models can be a regression, time series models like ARX model, RMAX model, Arimax model, Box and Jenkins model. Of course, you may be aware of all these names, but these are all basically regression-based time series models. The next type of mathematical model is artificial neural networks. So combination of dynamic and then static models also possible. So if you are not able to understand all the words which I am speaking, but keep them in your mind, okay, as it is getting recorded in future, it may be useful for you. So next one is some relevant problems while we are developing the input-output data-based mathematical models. Let me discuss first. So to develop input-output data-based mathematical model, we require input data, we require output data. Fine. If input data is clean and known to us, corresponding output data is also clean and known to us, okay, we use that input data and output data, develop a relationship. Maybe y is equal to mx kind of thing. So this kind of mathematical relationship is basically deterministic. Deterministic means you know everything about the input, everything about the output, developing a relationship. The other one is stochastic data, where there are certain compounds of this data which are not known to you. Maybe measurement noise, maybe disturbances, which you can measure, which you cannot measure. So what is this all about? What is this stochastic data all about? For example, you are sitting in an AC room. Let us assume that you are sitting in an AC room and you are trying to control the temperature of the AC room. So how are you controlling that temperature? You are using your remote, and then air conditioner is actually helping you. Air conditioner is helping you to bring the temperature at a particular level, to maintain the temperature at a particular level. All of a sudden, somebody is coming in and going out by opening the door. There is some hot air joining into the room, coming into the room, and it is going to cause some kind of variation in the room temperature. These kind of things are known as disturbances. That is one thing which I am talking about, disturbances. This disturbance, in your case, can be measured. So the other type of disturbance is like ambient temperature. In winter, the outside temperature is different. In summer, midsummer, the outside temperature may be 45 or so. In that case, under those circumstances, you are trying to maintain the room temperature. Of course, do you have any control on the ambient temperature? No, you don't have any control. That is the kind of disturbance we are talking about. When you are collecting data, there are certain things which are not there in your hands, but still, those things are affecting your inputs as well as outputs. So those are known as disturbances. Okay. So there is one more thing called as measurement noise. You are measuring the temperature of the room, and you are using very good temperature sensor. It is perfectly giving you the temperature. On the other hand, if you are using thermometer, probability is having plus or minus 0.5 degree accuracy. In that case, If you are trying to note down the readings, so your readings are as accurate as your thermometer readings are. Okay, so if you're measuring 50 degrees centigrade, there is a possibility of that reading maybe 49.5 or otherwise 50.5. This variation is known as measurement noise. So to appreciate the same thing what I was talking about here, I'll give a simple example. That is a bioreactor wherein you are producing all bulk drugs and then pharmaceuticals. Uh, for this, let me give you what are the input variables and the output variables. So this is a fermenter or a bioreactor where you are giving, basically in this case, what happens is you are having microorganisms feed into the reactor. Continuously, you are providing food to the microorganisms, okay, and you are taking the product out. To make it very in layman's language, very simple layman's language, you are having organisms, you are giving your good or jaggery, what we call it as, and it is getting converted to ethyl alcohol. Okay, so what is going in, that is jaggery solution, we are calling it a substrate. So you can either increase the flow rate of the substrate, or otherwise decrease the substrate flow rate. You can change the substrate concentration. So you can even change the agitator speed. You can change the water temperature which is flowing through the jacket of this vessel, so that you can maintain the temperature inside the vessel, which is also influencing the outcome. So water flow rate, water temperature, agitator speed, substrate concentration, substrate flow rate. These are the things which are actually influencing your product concentration, that is ethanol production. And one more thing that is actually changing when you are increasing or decreasing the substrate flow rate is actually level of the liquid inside the tank. So now, for the simplicity, let's not go into the product concentration. Let's pick up two things, that is substrate inlet flow rate and level of liquid in the tank. These are the two things which are very simple to understand for everybody looking at the participants. I'm picking up inlet flow rate to the tank and a level, otherwise height of the liquid inside the tank. These are the two things which I'm looking at. So at the beginning, when I start the experiment, so this is what I have seen. The liquid level is not there. I have increased the inlet flow rate. The height of the liquid has increased. See, the bottom graph is indicating the change in the inlet flow rate, that is a step jump. The top graph is indicating the height is slowly increasing and reaching a particular steady state. At that stage, it is going to be stable. Look at the figure as you are giving the inlet flow rate, outlet is continuously going out. So the height of the liquid is actually influencing the flow rate at the bottom. At particular height, the inlet flow rate becomes outlet flow rate. That's what actually is known as steady state. So that is what you see as a constant line after the top figure after 350 time instances. That is on the x-axis. If you look at the 350, from here onwards, it is almost steady. So what we have done here is you have increased the inlet flow rate here, and then outlet flow rate is changing like this. Oh, this is nice. So there is no disturbance, there is no measurement noise. This is what actually we see in textbooks, but in reality, this is not actually we see. You look at this. You have changed the inlet flow rate in the same way what we have done in the earlier case. So this is input data. Corresponding output data, if you look at, I'm going back by one slide and see, this is a simple smooth curve, no problem in this. But in the second case, you can see there are slight variations, up, down, and so on and so forth. Why is it happening? So is it reality? Reality is quite near to this. For example, in the same example, fermenter example, liquid is continuously falling in. You are asked to measure the liquid height in this tank. So you are looking at that height and trying to measure it. So as the liquid is continuously falling in, minus is going up and down. So you cannot measure it exactly. So you wait for some time. In our lab, normally we say this, okay, you measure the level. The students wait there for half an hour and then this cannot be done. He will take approximation. If it is the actual height is 30 centimeters, he will now down as a 30.2, sometimes 28.8 or so on and so forth. Those ups and downs are going to be read even in your online measurements also. That variation in the measured data, what you are getting is known as measurement noise. This is what exactly you see in this figure. This is the small variations in the figure is actually due to measurement noise. So we have gone one step ahead. First one is no problem, everything is deterministic. Now we said variation in the level with measurement noise we have incorporated. Now let's see next one. What is happening in this case? We thought that the input flow rate we have changed, and the input flow rate, how you change normally? The input is connected to some pump, and that pump is connected to electrical input. Of course, in our country, voltages are very steady. So there are going to be voltage fluctuations, so which are going to cause some kind of variation in the inlet flow rate. So what kind of variations we see there? In the graphical form, if you try to look at the bottom figure, look at the bottom figure here. This red line is indicating the variation in the inlet, the inlet flow rate, so which is actually having a lot of disturbances over here. It means the input data is not the blue line. In reality, the input data is this red line. You have these variations or disturbances which are there, which are influencing the height, okay? Which are influencing the height. This height, you can see here, which is getting affected by measurement noise, one thing. The second one is not only measurement noise is influencing this, but also input variations in the inlet flow rate is also influencing this. Means the output is getting influenced by two things. One is measurement noise, one is unknown, unwanted disturbances in the input. So now the next step is look at this. What is happening in this figure? Everything is also same as what we have seen in the earlier case. This is input data. The output data is, of course, got corrupted with measurement noise, and we got disturbance effects on this. And at a point 350, earlier we see level started with 0 and gone to 1 meter. All of a sudden you come down to 0. minus 0.2. Is it possible? So, for example, on the x-axis, what is indicated on x-axis is in time in seconds. Till this point, when you made a sudden jump in inlet flow rate, it has taken some time for the level to reach this point. At one point in, that is at 350th second, it has gone to negative, that to not even positive, negative, and then went back in the next instance. So what is it indicating? This particular data is indicating that whatever data point you got over here is absolute nonsense. It has no meaning at all. It's not going to happen in reality. What exactly has happened over here is while you are collecting data, there is something wrong which has happened. This kind of data point is known as outlier. So you try to develop mathematical models based on the input data and output data. You are trying to relate this input data and output data in the form of mathematical equation. These kind of data points are going to be a nuisance for you. So what you need to do is, first you need to remove this type of data. Okay, so this is known as data reconciliation. What were the data points? 4 or 5 data points prior to this. What are the data points after this? We try to consider that, try to remove it and put a new data point there and indicate that one properly. That's what is called as data reconciliation. But what I'm trying to impress upon here is you develop relationship between the input and output, having a lot of input data and output data. You need to look at what kind of data I have, whether the data collected is corrupted with measurement noise, or is it affecting disturbances or not, and what kind of inputs I have given and what kind of output I got. Look at this. So this is you're trying to control biomass concentration in the fermenter and the product concentration in the fermenter by using some controller. So what is interesting here is it's not like a simple level which we are talking about. Here we are talking about inlet flow rates, which can be measured at every instance. For example, every hour or every second, whatever it is, every 1 minute in the particular case. Actually, sampling time is 1 minute, I guess. But the output concentration, can you measure the concentration every second? Not necessarily. In reality, concentrations cannot be measured so frequently as we are measuring the level, flow rates, and temperatures. Concentration measurement requires you need to take a sample, take it to the lab, uh, put that one either in UV visual, or otherwise you can put in gas chromatography, or otherwise you put it in HPLC. Then after 15 minutes, you will get nice graphs. Based on that graph, you try to analyze it and then get the concentration. Means when you collected the sample, send that sample to the lab, get it analyzed, get the concentration, some time is going to lapse. Even if you are having automatic online samplers, that's going to take some time. Means the data is not available as frequently as the input data is available. What does it mean? Input data is available at every 1 minute, whereas the output data is available after every 12 minutes or 13 minutes or so. The problem becomes more worse when the people are trying to collect that sample and get the data. The same sample output concentration when you're trying to measure, that is being done by some human being, obviously there is going to be a few second variations, 15 seconds, 20 seconds, sometimes 1 minute, 2 minutes, based on the laziness of the person who is collecting the data. So this kind of data is called as multi-rate data. Multi-rate data means input is available at every 1 minute, output is available at every 10 minutes, 15 minutes, so on and so forth. The worst is irregularly sampled multi-rate data. Inputs and outputs are sampled at different rates, are having measurement noise, are having disturbances, and all this stuff are existing. By collecting such a data, you're going to develop mathematical relationship between input and output. This is actually is the reality. What we see in textbooks, you gave some step input and then output you got, that's not the reality. So to get this kind of variation, what we have, you need to vary the inlet flow rate. So you can see here, dilution rate is nothing but your substrate flow rate, substrate concentration, and this one is specific growth rate. Actually, mu max is specific growth rate. How is it actually changing? So what I'm telling you so far is, when I say develop mathematical models based on input and output data. So earlier you are seeing only U and Y here. The U is having all sorts of disturbances. Y is having effect of all the disturbances. In addition to that, you're having measurement noise. In addition to that, your samples are collected irregularly and multi-rate sampling. Now you need to develop mathematical models. So this is the state of the art. People are trying to look at multi-rate data-based mathematical models. In most of the cases, they're trying to use them. So rather than going into the depth of these mathematical models too much, what I'll do is I'll try to talk about Sweta, please switch off your mic. Sweta, please switch off your mic. There is some disturbance which is coming out. Okay. Now is next one is, you got this data. You are trying to deal with this data. If the data is obtained from a reactor, let us say. So what we are doing actually is, we are trying to develop an input and output relationship, and whatever decisions are taken by the human beings by looking at the input and output relationship has to be taken by mathematical models. That's what is artificial intelligence all about. So while doing so, we are dealing with data, and then how do you deal with this data is nothing but your data science, which I am talking about right now. So what I'm saying here now is inputs and outputs. Let's take an example of a reactor. So you are bothered about the production of the product, and then that is affected by inlet concentration and reactant concentration, so to say. And the second one is the temperature of the reactor. So inlet concentration is measured in terms of mole fractions or mass fractions, which are varying between 0 to 1. On the other hand, temperature variations are something like 27 degrees centigrade to 227 degrees centigrade. That is in Kelvin, 300 to 500 degree Kelvin. If you try to take these two as inputs and then try to get the output, which is again varying between 0 to 1, this temperature thing is going to dominate your math. Go wrong. So there's a problem in this case. So what should be done here is we need to bring all the variables into level playing field. So level playing field means what? So for example, for the same example which I am giving you here, concentration variation 0 to 1. What is the mean? Approximately 0.5. Okay, you subtract 0.5 from this, and then what is the standard deviation? Probably another 0.5. You just subtract the mean, divide with standard deviation, it will give you the data between plus or minus 3. Same thing you do with the temperature variations, find the mean. Mean may be somewhere near 400. You subtract 400 from both the values, 300 minus 400 and 500 minus 400. One is minus 100, the other one is plus 100. If your standard deviation is something like 33 in this case, you divide with 33, what you get here is a temperature in terms of plus or minus 3 and the reactant concentration again in terms of minus 3. Output also you do the same thing, output is also varying between plus or minus 3. So what I said just now is called as mean centering. What is mean centering? Take the mean of the entire data. Data may be 1,000 data points, otherwise 10,000 data points, doesn't matter. Find out the mean of all the data points of particular variable. Okay, you just subtract that mean from the actual data. You are getting mean as 0 now. So the remaining data after subtraction of mean value, what you get is mean 0. That's called as mean centering. Next thing is you try to take the spread of the data in terms of standard deviation. Means evaluate the standard deviation, divide the entire data with standard deviation. That is called as normalization. Mean centering and data normalization. That has to be done for both inputs as well as outputs to save the mathematical model. So this is known as, you are looking at the changing the actual data into mean centering and normalization. This is known as processing. Of course, data, when I say input data is also being done that way and output data is also being done that way. So mean centering means subtracting the mean, normalization means dividing with standard deviation, and this pre-processed data will have 0 mean, standard deviation of 1, and maximum and minimum values are varying between plus or minus 3 approximately. And of course, we need to remove the outliers. So this is what you actually use for mathematical model using straight away data. You can use it when they're actually quite near to each other. The magnitudes are quite, there's no problem. When they are too away from each other, in this case, it is better always to use this data pre-processing. Here, and let's repeat, we are processing input data as well as output data before we develop mathematical model. Then what we do, we try to develop or relate input, try to develop mathematical model. Once you got the outcome, then again, you need to post-process the data to get the actual outcome. So how to develop model? Here in this case, mathematical model, I mean relationship between the input and output. Inputs and outputs are mean-centered and normalized. This is already done. How to get actual output? So get actual output, you need to give to this mathematical model this normalized input you have to give. Mean-centered normalized input has to be given. So you'll get the mean-centered and then normalized output. So then what you do is you just multiply that outcome what you got with the standard deviation and add the mean value that will give you the actual output. This is how actually mathematical models at a higher level are being done. This is the actual output getting done. Give one more example here. Here we have a table. The left side table is having x values and y values. X values are 1, 2, 3, 4, 5, and then corresponding y values are 5, 7, 9, 11, and 3. Close look at this is actually the y is depending on x. Y is equal to mx plus c is the relationship. And you know, m value is 2 and then c value is 3. If you substitute that, that is 2 into 1 plus 3 is 5, 2 into 2 plus 3 is 7, so on and so forth. So if input data is like this and corresponding output data is like this, there is no problem at all, directly develop mathematical model. But in reality, the output data may be corrupted with the measurement noise, which is the second table. So x is same. Corresponding outputs which we are measuring by using some sensor is, in place of 5, we got 5.4. In place of 6, we got 7 is 6.6, and so on and so forth. When you try to draw the same thing, so look at these blue dots. These are the real-time data which we got. And we are having x on the x-axis and y on the y-axis, of course. And the intercept here is the c, and the slope is nothing but your m. What is that we are trying to do in case of regression? In case of regression, you try to develop, otherwise draw this straight line in such a way that if you try to draw vertical lines from that straight line to the actual data, this we call it as error, otherwise residuals, the difference between the actual data point and the mathematical model which you are using here. Okay, if you develop y is equal to mx plus c relationship, that relationship is indicated by this red line. So this error, this is E1, let us say, this is E2, this is E3, so on and so forth. All these deviations you are having, some of them are positive, some of them are negative. Sometimes if you are excited and if you try to add them together, you may get 0. So you are not supposed to add them together. What you are supposed to do is take the square of them, square of this E square, E2 square, E3 square, so on and so forth. Take the summation of all of them. Sum of the squares of the errors must be minimized. This is what is actually your regression all about. So you are trying to draw this straight line in such a way that some of the squares of the errors are minimum. So you can draw this line like this. Otherwise, if you draw another line which is passing through this blue line, this blue dot, and like this, another straight line, probably this is passing through three data points, but that doesn't mean that some of the square of the errors are minimum. So in case of regression, what we are trying to do is we are trying to develop a relationship in such a way that some of the squares of the errors are minimum. That is what actually is called as regression. This is the relationship which we are talking about. There are certain disadvantages with respect to the regression. So it is limited to the linear relationship. Even if you are having non-linear relationship, you can convert. For example, y is equal to e raised to x case. If you logarithm, natural logarithm on both sides, it will become ln y is equal to ln a plus b to x. That becomes on the left. On the one hand, you say this is y is equal to mx plus c. Ln a is actually c, and then b is slope, and x you can find out ln a and b, and then you can convert back. So this is basically non-linear relationship converted into a linear form, and then use the regression. These regression models, if you try to develop, okay, these are affected by outliers, all of a sudden changes in the data points, subjected to overfitting, like when you are having this, of course, is a straight line. Sometimes you may be using this kind of data. You use a curve which is going in the sinusoidal something like that. So that is called as overfit. So these regression methods can be obtained by using a simple least square method, which I was talking about. Otherwise, use a proper optimization technique by either linear optimization or non-linear optimization kind of thing. There also you will get the regression. But the solution which you are getting is may not be the same for all the cases. That's the problem here. So the biggest limitation here is the basic assumption that the data is normalized, which is not the case in most of the cases. So now, there are limitations for the regression. As I said in the earlier slides, the artificial intelligence, or otherwise replacement of human beings, are being made by using mathematical models. First, we try to use mathematical models in the form of regression. In the 1940s or 1950s, we realized that we need to go for the nonlinear relationships between the inputs and outputs. So there, the highly complex nonlinear relationships are represented by using artificial neural networks. So that's where actually artificial intelligence thing has come into picture. Let's look at the artificial neural networks more in detail now. So the outline about the artificial neural network goes like this. I'll try to introduce artificial neural network, and I'll try to introduce what is this neurons all about, what are intricacies of artificial neural network. I'll try to discuss about that one more in detail. And what are the various type of artificial neural networks which are being used, that also more in detail. So neural network, this neural network is essentially, as I said earlier, people are trying to relate the inputs and outputs. Fine. That relationship can be a mathematical model. In absence of this mathematical model, what were we doing earlier thousands of years? We are using our brain. Whatever input is going into our brain through our senses, maybe through nose, through ears, sound, or whatever, taste, whatever it is, touch. Based on this information, we are processing data, and then we are trying to react to that particular data which is going in. So essentially, our brain is actually mapping this input and output. For this particular set of inputs, we need to behave in that particular fashion. That's what actually we are learning for a period of time, from our childhood to today, whatever you are. When you are a child, if you look at some danger like a snake or the tiger, you just play with it because you are not aware of what to do with that input data, which is coming through your eyes. As of today, when you are walking down on the ground, if you see a snake, you will jump at least 1.5 feet and then run away from there. So why you are doing that? The data which is entering into your brain is telling you there is a danger, run away from there. Okay, this you learned over a period of time. This learning is done through neurons, which is actually fundamental building blocks of your brain. How many neurons are there in your brain? So 86 billion neurons are there. It's a huge number. Each neuron is connected to another 10,000 neurons, and all of them are working together to give you this information. This is basically a huge parallel processing unit which is sitting in your brain. So what human beings try to do is try to mimic this huge neural network which is called as your brain. So before going into this huge neural network, what I'll try to do is, let's pick up one neuron, try to replace that one with a mathematical model or mathematical function. How it works, let's try to see. That's what is known as simple neuron and perceptron followed by artificial neural network. Okay. In coming few slides, I'll try to explain how this human brain is being replaced, or at least people try to replace human brain by using artificial neural networks. Artificial neural network is similar to human brain. Computations are done based on the functions. Inputs are weighed for considering, and of course, weighted inputs are considered based on the bias. Of course, these details will come in later slides. Let's try to take a simple example here. So you got some input. That input is called as P. You are multiplying with input with W. P into W is giving you N. This N is processed by using a function to give you A. So the relationship between the input P and output is obtained by passing through this process. We are using a function over here. Okay? So this is a mathematical relation. So what we are getting as input is P. What we are getting as output is A. P and A relationship is developed in such a way that W into P is giving us N. N is passing through the F, which is giving us A. So for a set of inputs, for example, earlier case I gave you X values 1, 2, 3, 4, 5, so on and so forth, and Y values are Y is equal to 2X, let us say. When X value is 1, Y value is 2. When X value is 2, Y value is 4. When X value is 5, Y value is 10. So the relationship here is we simply multiplied these things and then added that function. It is giving us the output. This is the kind of simple single neuron. In this case, the output is a function of N. That function we have not yet decided. We'll decide that one later. This function can be either a linear function or nonlinear function, or different type of functions can be used. Essentially, we got input and we got the output, corresponding output after passing through this mathematical modification, which is multiplication of W and P, and that outcome, which is N, is passed through this function. Okay. Now let's go for the next one. Next case is, there are certain cases, like for example, you got 50 marks, you are passed, 51 marks you are passed, and 49 marks you have failed. So how do you decide this? Whether this particular model has to be used or not to be used can be decided by incorporating this B. This is called as some kind of threshold. When you take W into P, which is having a value which is above B or otherwise below B, depending on the requirement, if it is crossing, W into P is crossing some threshold, then and then only you give non-zero value to N. Otherwise, you give 0 value to N, so that A is going to be 0. So what we are incorporating here is neurons with bias, whether we need to use that particular neuron or not to be used for our purpose. That is decided by this bias. This bias is to be decided by you. When I say y is equal to mx is the relationship in case of a simple straight line, what is that we are trying to develop here? We know x data, y data, we are trying to develop the slope. That is m, trying to find out the parameter m. Similarly, in this case also, when you are having inputs, when you are having outputs, a function is there. What you are trying to find here is w. In the next case, what you are trying to find is b. Okay. So if you are able to get the values of appropriate values of w and b, now your relationship, if you are aware of the function. So what is to be determined in this mathematical model is w and b to get the relationship between a and p. This is the input, this is the output. Input-output relationship is to be developed based on the data sets of input and output by determining the values of W and B. Now, what is this W and B? So you have sometimes whatever input you are getting, okay, is passing through this process of multiplying with weights, comparing with B, and giving you N. This N is passing through this function and giving you A. Now let's look at this function. What is this function? This function is one of the functions is hard limiting function. So what it does is it takes whatever input is there with you, whatever input you are providing, it will give only two outputs. One is either 0, otherwise 1. In this case, hard limiting function is till this point it is 0, afterwards it is plus 1. Till up to certain limit, it is used when the demarcation is needed. Up to some extent of the value, it is going to be. After that value of value, it is going to be plus 1. So if you want to classify either pass or fail kind of thing, then you can use this kind of function. You will get 1 or 0. The other one is whatever input you are getting in proportion to the input, if you want to change the output. So in that case, you can use this particular function. This function is called a pure linear function. The inputs are changing from minus infinity to plus infinity, and correspondingly the outputs are also changing. This is another function. What is that we are talking about? We are talking about this particular F in the relationship. Okay, N and A relationship is passing through this function. That function can be either hard limiting function if you want to classify the data output, if you want to get the data in proportion to what is coming as input. The other one is a log sigmoidal transfer function. It will take inputs from minus infinity to plus infinity, but the outputs are going to be between 0 to 1. There is one more transfer function. It will take input from minus infinity to plus infinity, but gives you the outputs between minus 1 and plus 1. So based on your requirements, you decide one of the functions here. So you got input, okay, you got corresponding output. Now you have already decided the function, whether it is a pure linear function, transfer function, any transfer function which I have just now discussed, and get the values of W and B, then you got the relationship. This, however nonlinear the relationship may be, you can map these two things, input and output. Now, till now I talked about only one input is influencing the output. In given case, more than one input is influencing our output. So like, let's say there are R inputs, P1, P2, P3, all of them are influencing your output. In the fermenter example, inlet flow rate, inlet concentration, coolant flow rate, coolant temperature, coolant concentration, agitator speed, catalyst flow, and organism flow, so on and so forth. All of them are inputs. If you are having such input, P1 to PR, what has to be done? So each one of these inputs are multiplied with the corresponding weights. Take the summation of all of them, okay, and compare that summation with B. If that summation is crossing this threshold, then get the N, pass it through the function, you will get A. So what we are doing here is multiple inputs, single inputs are mapped. This is also another neural network. What we are supposed to find here is a vector of W's, weights, and corresponding bias. Then we'll get the relationship between A and P1 to PR. Rather than writing P1, P2, P3 every time, we can put a dark block. You can put a dark block here. Okay. So this is a simplified notation. Basically, you are taking W and then P, multiply them together to give you some value which is compared with the bias or added with bias, and that is passed through the function that gives you the outcome. So multiple inputs, single output. You got a neuron. So only one function here. This is known as single neuron, which is giving you the output. Rather than having one input and one output relationship, maybe having more than one input and more than one output. You wanted to develop a relationship between these two. In that case, you are looking at P1 to PR, and you have a vector W, which is getting multiplied with P1 into W11, P2 into W21, P3 into W31, so on and so forth, and add them together. Each one of these lines which I am drawing, P1 to this first sigma, first neuron, are multiplied with corresponding weights, That summation is compared with B1. Now whatever you got there is N1. This N1 is passing through the function and giving you A. On similar lines, each one of the P1s, P1 to PR, are multiplied with corresponding weights and taken the summation of all of them compared with B, and then you'll get the N2. This N2 is passed through the another function, you'll get A2. Similarly, if you're having S number of outputs, similar thing is being done. So what is the difference between this one and the earlier one? The earlier one, you are having only one output and multiple inputs. Now in this case, you are having multiple inputs. At the same time, you are having multiple outputs. You are trying to model the relationship between the multiple inputs and multiple outputs. What is that you are supposed to do here? You are supposed to determine the values of weights and corresponding biases. If you are aware of weights and biases, weight is actually, here in this case, weights is a matrix and biases are a vector. So you use them to get the relationship between P and A. Of course, F is already decided by you, whether it is a pure linear, sigmoidal, tan sigmoidal, log sigmoidal, okay, hard linear. Those are the functions which you can decide depending on the situation. Okay, so now you got the relationship between the multi-inputs, multiple outputs, but you are having few neurons arranged in single layer. So this is single layer input output based network. Now what we are doing, look at this. Look at only the first layer. What we are doing here is P1, P2, P3, so on so up to, these are all inputs. Each input is multiplied with a corresponding weight. You got the summation compared with B1 going into the F1, it is giving us A1, right? On similar lines, for the second neuron in the first layer, you got A2, third layer, fourth layer, so on up to S number of neurons are there. They are giving you A1, A2, A3 up to AN. Now, forget about the first layer. You are having, assume that only second layer is there for the sake of understanding. What are the inputs for this? In place of P1, P2, what were there for the first layer, you are having A1, A2 for the second layer. The remaining procedure for the second layer is same. That is, you take A1, okay, multiply with corresponding weight and give it to the summation. A2, second weight, go to the summation. A3, so on and so forth. So all these A's are multiplied with corresponding weights and then take the summation compared with B2, okay, and it goes to N2. That will give us A2 over here. On similar lines, you are doing for everything. Like, our only difference is earlier you are having P1, P2, all the inputs. In place of P1, P2, you are getting A1, A2, A3, single primes. And in the second case, output of second layer is A1, A2, A3, A2, A1 prime, A1 double prime, otherwise A1 2 it is indicated. Anyway, so basically, in place of simple inputs, you are getting the outputs of the previous layer as inputs to the second layer, outputs of the second layer as inputs to the third layer, and outputs of third layer is actual output for you. So what we got here is multiple inputs, multi outputs, and multi-layer neural network. Okay, these functions are mimicking our neurons in our brain. So you have quite a few neurons, or otherwise few functions are intermingled and interconnected to give you the final outcome. So however nonlinear your relationship between the input and output may be, we can use quite a few neurons and try to develop mathematical model. So you can see what we are getting here, that is A3. This is nothing but coming from the function F3. Okay, the input to the F3 is nothing but N3, which is nothing but your A2 multiplied by the weights and then added with bias. So you can see that added with bias is B3 and this entire bracket, so on and so forth. That is actually what is being done over here. Next one is, rather than writing all those inputs separately, we are writing in the form of shortcut notation. So rather than writing P1, P2, P3, we are writing a block here and so on and so forth. This is multi-input, multi-output, multi-layered neural network. So when you give some input here, that will pass through all these parameters, namely weights and biases, gives us the first layer output. That first layer output goes to the second layer. So that gives us second layer output. Second layer output goes to the third layer and gives you the final layer output. That's what actually is the output for us. Now, there is something called as ANN learning. What is this ANN learning? All this is possible only when you have the values of weights and biases. From where we get the values of weights and biases? This determination of weights and biases is known as learning of artificial neural network. So how is it being done? You collect huge set of input data and output data. Okay, arrange them properly and present a set of inputs and corresponding output and try to adjust the weights and biases. How do you adjust this? Look at the output. What you are getting to, you assume some values for weights and biases at the beginning and pass P, that is inputs to this network, you will get some output. You compare that output with the actual output, corresponding output, experimental output, you will get error. You try to backpropagate that error in such a way that go on adjusting the weights and biases towards the input. So essentially, this is a feed-forward network, that is inputs are processed in the forward direction to get the output. And we are trying to use an algorithm which is adjusting the weights and biases in a backward manner. That's called as backpropagation algorithm. So feed-forward network with backpropagation algorithm, that's what we call it as. Essentially, what we are trying to do here is the outputs, which are basically experimental outputs and then predicted outputs, we are comparing them together and trying to take the sum of the squares of the errors or so, or otherwise optimize these weights and biases in such a way that the decision variables here are weights and biases and trying to reduce the or minimize the error. That's what is known as training. I will try to give you a glimpse of what is meant by training. So procedure for modifying the weights and biases are known as training. Also, we are trying to use a few algorithms, optimization algorithms here to get the best possible weights and biases. Learning can be classified as supervised learning or unsupervised learning, because supervised learning network to move the output towards the target, whereas unsupervised learning, this is entirely different. Actually, this is called as a clustering algorithms, etc. So we have another 15 minutes. I think I'll try to, rather than going into the details of this learning and then training algorithms, what I'll do is I'll try to give you other type of networks also which are available with us. Okay, what we try to do is we try to see the output, and then if the deviation is there, try to propagate it back in terms of weights, biases, and so in the process, if you try to use raw data, you're going to face a lot of difficulties. What you are supposed to do is you pre-process the data, you try to remove outliers. If you don't remove outliers, what happens is, in case of training, it is something like this. You presented some set of outputs. Okay, you for the given set of inputs and outputs, the outputs are deviating something. You adjust the weights and biases. Now you present another set of input and output, which is actually outlier in the output. So what it does is it will show you a lot of error in the output. Because of that, weights and biases are disturbed too much. When you are presenting other sets of data, again you have to start from square one. It's going to take an ending process of go on training. See, I tell you, my experience way back in 1997, I guess. Yeah, I think in 1997 when I was using this neural network. In those days, the machines are not your Pentiums or something like that. I was having some 386 machine or 486 machine in those days. I used to give this input data and output data. At the end of it, I used to come back and then see whether the required error minimization has taken place or not. It used to take something like 3 to 4 days for training. So in one instance, it was taking more than 1 week. Then I realized something went wrong. Rather than giving data as a 0.1, I unfortunately gave it as 0.01 or something like that. One decimal point was missing. So it has disturbed the entire thing, and the work which is to be done 3 days has taken more than 7 days. And then I realized then another 3 days. It has taken too much of time, almost 10 days to train the network. Of course, so the same can be done in less than a minute nowadays with the computational power what we are having as on today compared to what I was having in 24 years back. But still, that outliers have to be taken care of. So what we are trying to do here is we are propagating the error back and adjusting the weights and biases. That's why it's called backpropagation algorithm. This is the algorithm. Of course, various type of optimization algorithms are there. variable step solvers are there, single step solvers are there, accelerators are there, weighted back propagation is there. There are different algorithms, which I'm not going to concentrate on that. I'm not talking about this one also. So there are certain examples, simple examples, which our students have worked in the period of time. So you have viscosity, flash point, pour point, and then lean point. You just measure them and try to find out the concentration of kerosene petrol. That is actually some adulteration was taking place in those days. It was predominant earlier, 25 years back. We try to get the simplest possible method to get this. We train neural network and then try to take a sample. Within half an hour, you get this, and then you can take action on that. The other one is like wastewater solid waste management problem, where we are all now sitting in Gujarat, probably many of us, longitude and latitude, where the location is. For example, in South Gujarat, in a given town, the solid waste which is getting generated is entirely different from North Gujarat. And similar lines, what is getting generated in Kutch may not be getting generated in Kheda. So you need to take the location in terms of longitude and latitude and present population of the town, population density, economic parameters, social parameters, all of them are actually influencing the generation of solid waste and then its quality and characteristics. So we try to take the above ones, that is longitude, latitude, population, economic and social parameters as inputs. We try to predict the solid waste generation in each one of the community for medium scale towns, 120 medium scale towns, and 185 small scale towns in the state of Gujarat. And we try to map where actually we can develop the solid waste dumping sites. So that's what actually one of my students has worked on. So this kind of work can be done in this. Next. Of course, in the case of control also, we try to use this. You're having manipulated inputs and then controlled variables, fault detection, diagnosis, and classification type of neural networks are also going to be used. So now let's go into the next one. So that is when you're saying that pattern recognition, there are two types of networks which are available other than this, what I have discussed now. Whatever I have discussed so far is known as feed-forward network with backpropagation algorithm. The other one is like the network which I taught right now was static network. Steady state data is given, steady state data is used. If you are having dynamic data, in that case, how do you deal with it? So in that case, you require enough networks. The other one is you just show 20,000 faces and then you put one more face. Well, this fellow is from northeast or otherwise southern part of our country. Your network must be in a position to recognize that. How do you do that? These are the two things which I am going to discuss right now. So these are known as recurrent networks. These are having different type of geometry. I'll tell you here rather than going into the details because of the time, lack of time. We're having only 12 minutes. So this network is looking similar to what we are having earlier. Only one exception is, for example, you are giving some data at 10 o'clock. Okay, you got the output for that. So you use that output at 11 o'clock along with the 11 o'clock input data to get the 12 o'clock data. Essentially, when you're trying to use mathematical models in a dynamic scenario, what is happening into the next instance has to be determined. That is called a dynamic model. This Hillman network essentially tries to do that. What it does is y at 11 o'clock can be obtained by taking y at 10 o'clock, that is output at 10 o'clock, and input at 10 o'clock. What does it mean? For example, if you're having simple level in a tank system, level you're trying to measure, inlet flow rate is there. If you allow the inlet flow rate, otherwise if you open the valve, that flow rate is actually influencing the output. Okay, so previous height of the liquid in the tank is definitely going to influence the height in the next instance, like 10 o'clock, otherwise 10 o'clock height is there and 10 o'clock flow rate, and 11 o'clock height is influenced by 10 o'clock height as well as the 10 o'clock flow rate. This is what actually we are talking about. Y of k plus 1 is influenced by y of k as well as u of k. So that kind of dynamic models, if you want to develop, in that case, this dynamic connection, this is also known as recurrent connection, is being used. The training of this network is done the way what we are training the feed-forward network with the backpropagation algorithm. In that case, you simply remove this feedback connection, you give appropriate inputs, get the outputs, and go on training this. Only exception is rather than giving only U1, U2, U3 up to all the inputs, and then you give that Y1 also. One of the outputs has to be given there. So that will suffice the requirement, and then try to optimize this. That will give you the outcome. This is known as Hillman network. Hidden layer has tan sigma transfer function. Output layer may be having pure linear functions. These functions can approximate discontinuities also. That is the advantage. Okay. If the relationship is complex, then hidden number of neurons can be increased. So in case of Hillman network, the delay in recurrent connection stores the information about the otherwise information required from the previous happenings is stored in this. This is similar to ARX type of model. So this is, if you are trying to predict the dynamic scenario like your stock market, ARX models, RMAX models are being used. This recurrent kind of networks can be used for that dynamic prediction purposes. So this in this the presentation, I have given you the what code required for development of these models. If you are interested in, you can do use that. Okay, next one is Hope-filled network. Another 2-3 minutes I'll take, and then I'll leave it for question answers another 5 minutes. Let me explain this one as well. In this case, this network stores the equilibrium points. This is not the way what we are looking at earlier. This network is something different. So you give inputs, okay? These inputs are producing some output after multiplying with weights and then adding with bias, and is coming and passing through the function. You'll get some outputs. Now, these inputs are removed. The outputs are fed back into the network as inputs. What happens here is, for example, if I'm getting 10 over here, after feeding back, probably I may be getting 9.5. Another run, go on reaching. After some time, you will reach a value which gets stabilized. So that particular point is called as equilibrium point. Means when you are presenting something to this network, it will try to reach an equilibrium point in such a way that it will stabilize somewhere. Okay, this is known as Hope-filled network. So this network basically uses various type of functions like satlin, etc. So what we give here is initial conditions, and then output is fed back to the become input, and while you are training it also. So this is the way of training it. You just see this. Let me explain over here. At the beginning, you presented something like to give you a simple example, a layman's example. You got something like 10,000 people from Africa. You got their photographs, and then you trained your network. Then another 10,000 photographs from India, you train the network. From Korea, you train the network, and some European countries, you train the network. Whenever you are presenting Africans, it will form an equilibrium point. For example, this is an equilibrium point for the Africans. This is an equilibrium point for the Koreans. Now, if you give a new data, maybe a photograph, which is coming from Korea, so that will, what happens, this Korean photograph may be over here, and this will need to move towards either this equilibrium point or the other equilibrium point. So obviously, the photographs which we are showing earlier for the Koreans is forming this equilibrium point. Obviously, the network slowly collapses into equilibrium point. This is known as pattern recognition. So this is the thing which has been used for the recognition of culprits in Rajiv Gandhi assassination case way back in our institute. We are trying to use this kind of networks in our research laboratory. One Dr. Majumdar has done this work. Okay, so these are the 3 types of networks. First one is simply input-output relationship for the steady state. Of course, dynamics also can be used. That is by modification. The next one is Hillman network, where it can be used for the dynamic scenario. The third one is classification, or otherwise recognition of face or something like that can be done by using this Hope-filled type of networks. What we have done in this lecture in the last 60 plus 25 minutes, that is 85 minutes, is we try to look at what is meant by artificial intelligence, and then where neural networks are standing in case of artificial intelligence, and then what is data science basically, and what are the problems related to data, how do you deal with data, what kind of problems in the sense measurement noise I talked about, disturbances. So essentially input and outputs are not very clean, they are disturbed, otherwise they are having problems. We need to pre-process the data before we use that one for the development of input-output relationship. Once you got that, earlier relationships were simple linear ones by using regression. When the nonlinear relationships are existing, to get those nonlinear relationships, we try to use artificial neural networks. And nowadays, we are trying to improve upon the hidden layers. See, when we talked about artificial neural networks, it's a part of machine learning. We are using machines to learn huge sets of data and try to develop neural networks like determining the weights and biases. Now, what we are doing is the data is very huge and relationships are very, very complex. To do that, you require more number of neurons inside the network. We are trying to develop algorithms in such a way that the hidden layers in the neural network, going back to the network. So this is a 3-layered network. If rather than having a 3-layered network, if you try to use some 50 layers in between, and each layer is a different type of algorithm. So this will become, the depth of the network becomes too high. So this is known as the deep networks. And learning of, otherwise developing the weights and biases for this network is called as deep learning. So you heard about artificial intelligence and the neural network, then machine learning, and we are talking about deep learning. Deep learning is actually advanced version of this artificial neural network, which is having quite a few neurons and then advanced algorithms combined together with multi-layered neural network. Okay, so that's what is about deep learning all about. So what we got here is a glimpse of all of them. So I talked about artificial neural networks, wherein you can use the inputs and output for the static relationships, dynamic systems, classifications. All these things can be done by using artificial neural networks. Then the present and then future, that is basically what we are working on is deep learning, and using these deep learning algorithms to get the disease and then human profiles, etc., health profiles, and then trying to find out the drugs, etc. So this is what I wanted to say about the artificial intelligence. Of course, in 1.5 lecture, we cannot cover all the world's knowledge. Whatever can be covered, I try to cover that much. If you have any doubts, 1 or 2 questions I can take. I think we left with only 2 minutes time.
Thank you very much, sir, for your wonderful session, starting with different terminologies that is used. We are not aware of that terminology, but after your lecture, hopefully every participant will be knowing what are the different terminologies which are there in this artificial network, as well as in case of data science. There is one question in chat box. I'll read out that: how to set optimum number of neurons at each hidden layer in MLFF network?
Okay, multi-layered feed-forward network he's talking about. See, earlier days, in almost 2 decades back, when we were working on neural networks first, this is trial and error. In most of the cases, those who are using neural networks, even nowadays also, they are using the same thing, same trial and error method, like go on increasing the number of neurons, as and when you are getting the sufficient required minimization, great. So you're done with it. But there is a possibility of using optimization technique again. So the optimization used to determine the weights and bias. On the top of it, one more optimization layer used to optimize neurons. That is also possible. If you have tried, if you try, you can try it that way. So in layman's language, in many of the cases, people are still looking at a trial and error method. Here you can go for optimization, 2-layered optimization. That also is possible.
So another question from my side: that is there any limitation for input data that I should have? That already you told that it is a trial and error method, but
there is no limitation. There is no limitation on the amount of input which you can give.
Okay.
Okay, a training thing I have not talked much because of the wanting of time. What we try to do is we try to develop input and output. For example, steady state inputs or steady state corresponding output. Okay, you may be having 100 data sets. For example, a given input corresponding output is there. Now you give some new input corresponding output is there. Like that, these are all batches you are providing. For this point of input, this is out. This kind of input, this is out. The way you are weights and biases when projecting, otherwise presenting new data set, obviously your weights and biases are going to change. That's what actually your we call as a learning process is all about. So you need to optimize the learning process in such a way that weights and biases be determined in such a way that all the what we say presented data sets combined together, the error must be minimized. Now, if you are having more amount of data, which is corresponding to the same system, the accuracy of the weights and biases will increase. It's not going to affect you. And in the process of giving that, if you give one outlier, it will spoil the entire network. So more data is not going to spoil you. More data is going to help you improve upon the weights and biases. Of course, it's going to take more time for training.
Sir, according to you, what is I can say better if I want to develop network regarding drug development, supervised learning or unsupervised learning?
That depends. Both are possible and feasible. In supervised learning, what happens is you are providing the input and the output data. Okay, so batch data kind of thing you are giving. The targets are looked at and tried based on the errors which you are getting. Okay, so you are trying to get the weights and biases adjusted. That's what is actually supervised learning. In case of unsupervised learning, that Hopefield network which I was talking about, you present the data, it will collapse into one equilibrium point. That is unsupervised. Okay, it will reach one equilibrium point, the other equilibrium point. In case of in a layman's language, I'm not expert in pharmaceuticals, but let me tell you, if you are having drug A, drug B, drug C, okay, so when you are having Hopefield collapsing into drug A, okay, that is selected by drug B is selected by that. But whereas in case of symptoms, when you are looking at the fever temperatures are coming down for this, if I give this combination of molecules and then the temperature is actually 101 to 99 coming down, so that input-output database networks are also going to help you. That depends on the requirement which you are trying to do it. Supervised learning is basically the steady-state purpose, whereas pattern recognition, you can go for the unsupervised Hopefield type of networks. Dynamic scenario, you can go for the Hillman network. So if you're having a set of molecules, you want to get a set of parameters, then supervised feed-forward batch propagation algorithm will work for you.
Okay. Sir, you were telling about that pattern learning and picture
pattern recognition.
Pattern recognition. In case of again, I'm repeating my drug example. If I have a 3D structure of my drug, and I can use that in that model, pattern recognition model?
Probably yes. This is an open question. Probably anybody has used it or not, I'm not sure. Yes. At the bottom line, you can use it, yes.
Okay. So, last question, sir, fine.
If anybody else is having questions, they can ask, no problem.
Sir, thank you very much for your time.
Okay.
I'll be presenting you an e-certificate.
Okay, fine.
Please accept
this...
from our side.
Okay.
Thank you. Thank you very much.
I hope this lecture is useful for the audience. Thank you for giving me an opportunity. Thank you. I'm doing this. Okay.
Thank you, sir.
Okay.
To participant, today's all session are completed. Tomorrow we'll be starting with at 10 a.m. with Mr. Jitesh Joshi's lecture. Attendance we are taking using Google Meet extension, so attendance will be covered. It will be time wise it will be covered. At the last day, we'll be having one exam that we'll be taking mostly via Google form, and feedback also will be taking at end of our 5 days session. We have kept one feedback session at the on the 5th day. So on 5th day, the first lecture is of mine only. Sandesh sir, if you can mute yourself. So at the end, on that 5th day, we'll be also having some interaction with each other on 5th day. So you will be introducing yourself. So there will be introduction will be there. Hope today was a fruitful day for you. Thank you very much for your time. And PPT, we have consulted with all speaker. If they give, for example, the Rao sir PPT, he has given consent, so I'll be sharing that to your email ID. So we are taking consent. If they give consent, we'll be giving you PPTs also. No problem with that also, right? Thank you very much. We'll meet sharp at 10. So I'll request you to join by 9:50. 9:50. Thank you. You can leave the meeting. Thank you.